relax. Okay, so we can. Yes, I think we are almost sort of here. So I would start. So I go to let me switch off the phone. Okay, so this afternoon I will dedicate most of the time to look through different methods that may help you in formalizing some system. Of course, the time is very short. If I would discuss each of the methods in details, this will require more than 3 hours, more than one lecture. But I would like to go through these methods basically to give you first insights of each of the methods, also because you may interpret them as exemplary cases, good cases. I'm not saying I will select it randomly, but it's a good case that represents what you may need during the engineering of a system through the life. Yesterday we were relying on the. Can you still hear me now? Just to check again, be sure. Yes. I suppose so. Okay. So yesterday we discussed in a broad sense the fact that when you develop a system, if you want to follow a structured approach, you may have some model in mind. One model I was suggesting was this one about life cycle model that tells you of different stages or phases you go through, and in each of the phases you need some activities to be done to achieve some result of the phase. No? And in these activities, you may have a support from the methods, modeling methods. In principle, the methods I will tell you today may cover the identification, concept, requirement, and design. So this tells you a little bit about some good cases in each of the phases. Of course, you may reflect on the idea I already told you yesterday. I would like just to summarize as the main concept that we discussed yesterday. Just a second. I can see what you can see here. It's not on. Okay, but I don't really see that can happen. So I'm losing time. So yesterday, let me tell in general. I will use the blackboard, but I'm writing almost nothing.
So start with the
Where is it? Yes.
The blackboard.
Okay. Okay. Yes. Thank you. So now the blackboard is. So what we discussed yesterday was a kind of flow in terms of reasoning. We identify problems. We state the purpose, potentially more than one. We develop some kind of definition of what is the real value we will get from the system. Not a matter of cost, it's a matter of what you can get as a benefit from the system, from using it, from experiencing the system, and so on. And we were saying that this is a first consideration we may do when we are identifying and conceptualizing the system. It's a strategic understanding. It relates to the system, basically considering what you want to have from the system, from the engineering. To consider also some aspect that is important in this phase, we may talk about functions which are telling you what the system is doing. Let me remark one matter in this, just in summary, about the fact that yesterday we were talking about boundaries, the definition of boundaries. I was general in the sense of saying we may have some key variables upon which we can act within the boundaries, and we may have some other variables that are part of the environmental, say, domain where the system is used to operate. If I want to have a specific perspective, which could be typical perspective to fix a boundary, we can fix boundaries in terms of functions that the system is doing. So the variable is the functionality. I'm following this reasoning because basically in the modeling method I will tell you, I will use functional modeling also in this stage. So when you are defining the boundaries. Functional modeling is not only in this stage. Yesterday I told you we may start from high-level functions, but then we can go down a level, breaking down the function in sub-functions to have more details. So if here we were talking about what and why, and we discussed yesterday, from now on, let's say when we break down the function and sub-functions and we go ahead with the design, we are talking about how to do it. Okay? So this is basically the interface in the reasoning we're doing. So following this, according to the general model, problems, partials, values, and high-level functions in terms of boundary definition regards identification and concepts. So in these stages, as I told you, it's the matter of understanding what you need, what you want to achieve, what you want to evaluate as a good benefit when you are deciding if it's good or not. You're not evaluating yet, but you're fixing somehow the targets. And so when we're here, we're basically dealing with these concepts. Yesterday I told you the concepts. Today we see how this concept may be implemented with some modeling method. We could see until functions in the first part of the lecture. And then we will move ahead. Let me write down without specification from functions to objects. We will tell you later. But we're moving from some stage where we're having an understanding from the functional point of view to another stage where we're more understanding from the point of view of objects that are carrying out something. Okay? So this is about the how when I'm engineering the system. But now in this first part, I'm going to concentrate basically in this part, problem, purposes, values, higher. That's my concentration now. But it's hard to let's say, to move through these all methods in a while, in a short overview. I will try to give you the basic fact of each method. Let me say in general the origin, because you will see that I'm collecting methods that comes from different domains, from product development, new product development, from software engineering, from, let's say, business and economics in terms of decisional problems. So you understand that there is a broad set of domains where these methods may come from. I see from the overall perspective of an engineer that wants to engineer a system. So the product is a system. A business system is a system itself. So you understand that you may have a generic perspective on the methods to understand from each of them some kind of support. Purpose and so I will concentrate first in this identification, purpose and boundaries, and concept, functions, and values. So basically, these are the terms I will discuss through the method. The modeling method, let me give you another consideration more as a forward. The modeling method is something that can be intended as a language, modeling language. You have, in the language, you typically have some constructs. Think about the natural language. You have verbs, you have nouns, So these are the constants. Of course, in the modeling language we will talk about, we will see each of them some constant. And beside the constants, you're having the rules to combine the constants. So grammatical rules. Now we have to think about the rules, the logical rules you combine them. So this is generally valid. Then, more specifically, some of the methods you will see are also having the graphical symbols. So the constant has a symbol. So in that sense, when I'm talking about the symbol, I'm talking about also the constant. When I'm combining the symbols, it's about talking about the syntactical rules to combine them. That's the model. Okay? So in general sense, a modeling language can be iconic based on symbols or also textual. So in that sense, you have some rules to conform to. Okay? So then, of course, this was the general consideration to say that we are looking to formal models. We need some formal rules, some formal constants to build the model. Of course, some models may be also less formal in the sense that they are less defined or a little bit undefined in the syntax. But it's a matter of the range you have in terms of languages that you can find. Said this, let me discuss a little bit a first case. My discussion always will be, as said, I tell you a little bit the origin, I tell you the constructs and way to combine the constructs, I tell you some idea of application in the life cycle. That's the way I will do it. Okay? Any of you has already heard about IDEF0? Who? Just to have an idea if it's new or not. It's new to you all. Good. So I'm providing you at least some additional value. IDEF0, as an history, originates from a prior method which was named just an information SADT, Structured Analysis and Design Technique, but it's just a detail. It's more important to say that it results as it was commissioned by the US Air Force. The US Air Force was commissioning this kind of method to enable a simple way to represent activities and, let me say, in general, functions. We will talk about functions in an organization, in a complex system. Okay? So you may understand US Air Force may deal with not only the fact that we have a technical system, but we have a fleet, we have the logistics related to the fleet of airplanes. No? So it's clear that the level of understanding of the problem relates more to the logistics issue. And of course, it is related to each of the complex technical systems, which is one airplane, but it relates also to other resources, crews, hangars, whatever. So it's clear that if you think about the need, we need to have some tool that enables to scheme in a simple way what I'm doing in this organizational system. Okay? So said this is just trying to interpret a little bit the need. I was not in the head of the people that were commissioning this, but I see, let's say, as a result. I came in contact with this IDEF0 first time when we were doing some work more than 20 years ago with and NIST is the US National Institute for Standards and Technology. IDEF0 was first built in this context. National Institute Standards and Technologies of the United States were developing, according to the mission of this institution, standards like IDEF0 is not standard. Indeed, you can find this available as a standard in terms of standard requirements, documents that tells you how to build IDEF0. I was placing a reference if you want to move in the web and look at IDEF0 and look for documents and so on. Okay? What is the aim of IDEF0? Representing a system typically an organizational system, in terms of functions. So the function is, if you think about the idea of a function, if we give a definition, is an elementary activity, more or less, could be also a little bit a macro activity, depends on the level of detail you're looking at, but let's say it's an activity that transforms some input into outputs. Transform. Think about the production process. You're having the raw material, you're getting to the finished product. So you have some functions, activities that transform from raw material to finished product. That is the idea, let's say, of transformation. But transformation can be applied to many methods. So functions can work upon materials, energy, financial flows, people flows. Vaccination, you're transforming a person from before vaccination, not vaccinated, to vaccinated. So it's a transformation as well. So functions tells you about the transformation of some objects, let me say, that change their own characteristic starting from input and getting to the. Okay? This is quite general.
For the case of the vaccination project, what language have you used in this case?
No. I was not using edit here. It was just to say that also the vaccination case may be interpreted as a set of functions that require the transformation.
Yeah, but again, I'm not sure in the other class is all of this language.
No. It was not. I was not looking at this detail, but it was not. Okay. So now, said this, go back to the need, so to contextualize a little bit the use of wider theory. We need a system to analyze, a method to analyze a complex system, breaking down the functions that this complex system can play. First. So an analysis need. We need a system that, a method that enables to communicate such understanding, such analysis to others. The first person with whom you're making a communication is the expert that is interviewed to get from him the mental model. Remember always that each of the experts may have its own mental model, its own beliefs. You are trying to formalize the beliefs about functions of a process into a formal. So the communication first starts with the expert that is participating to the model building. It's participating because it provides the knowledge about it. You imagine to be the analyst, you don't have the knowledge of the process, of the organizational system. Okay? Here, the second target of communication is, in general, say, a set of stakeholders that should be informed to create a consensus. It's not exactly the expert you interviewed, but is a set of targets that may be interested to share the model, so to have the idea of having a formal model to represent a consensus among different experts. Okay? So for these three reasons, analysis in terms of functional model, communication direct with experts or indirect with those interested in this analysis, would bring to a language that is simple. The simplicity of target zero is the most of the value you can get from target zero. That's the point. Okay? And you will see, and I will tell you in a quick way, because it's simple, you will see that the modeling concept has very few. The rules, I will not tell you all the rules because of time, but they're not so many. In the end, the modeling language is simple. First, let me move a little bit ahead just to look at this picture as example. The first consideration is that we have a so-called function in terms of, say, element to be modeled, represented by a box in the graphic form. Okay? So any box we may find is representing what function is performed by the system. Okay? That's it. So a lot of boxes will be a list of functions that are performed by the system. The other construct is represented by arrows, this one, or these ones, or these ones, or these ones. You see, for some reasons, that they are placed in different parts of the box. This is about the rules. But in the end, if you see overall, the arrows are a way to interface this function with other function. It's an interface. Let me explain a little bit better without looking at the meaning in the moment. But this function is making overall the manufacturing of gearboxes. Let's say. It's clear that it's a macro function, it's not in detail to elementary activities. But of course, this tells you that to make the gearbox manufacturing, we need some element that should be available to be performing this function. Okay? These elements are represented by the flows, all these flows. The one that enters in the left, the top, and in the bottom part. So what is needed is not the question only of what are the functions of the system, but what are the factors that should be guaranteed, available to carry out the function. What are the needed factors? And so these are the needed factors, the one that comes in these places, top, bottom, and left, in these arrows. Of course, the other factor, it's more, let's say, to know what a function is achieving, that is the outcome. But you may think also that this may be an interface to another function because this outcome may be on its place factors for the function that is receiving the outcome. Okay? So this is most of the idea of IDET 0. I'm done. Parts of details. It's quite easy. There are details. But in the end, think about what I told you. First of all, you have a modeling concept, which is the functional block box. And it tells you about any function that can be carried out in a system or by a system. Okay? I am saying in a system or by a system, depending on the context you consider. The car is providing me, is doing some function for me as a car driver. Okay? So in that sense, let me say it's the function that is performed by the system, some boxes. And also what is needed to perform the function, the factors you see as flow in out. Okay? Clear? In general, for the analysis, not only answering the question what are the functions to be performed, what are the factors needed related to the function to make the function, what are the outcome of the function, but also you can use this representation to ask yourself what is done well, what is done in the right way, what is done in the wrong way. It's a little bit a follow-up of the functional schema, but just to tell you and enlarge a little bit the consideration. You may represent function because you may somehow scheme out that this could be improved. This is not reaching what is expected in terms of functionality. Say this, I told you basically the major idea. There is one major idea which is, let's say, general. Here you see a particular case. The general concept, when you have complex system, you need some way to reduce the complexity. No? This is the general concept. The general concept that is used typically in this modeling language is hierarchization. We play hierarchies. Hierarchization is, in this case, a kind of not the only one you can build. Okay? So, hierarchization means that, of course, you start from a high-level description in the model, and you break down into detailed breakdowns. Okay? In this case, the breakdown is done in terms of functions. So it is a kind of iterative process because if you start from the beginning, from the top, you have one high-level function. If you break it down in a bottom level, you have 4 functions that are the breakout of the high level. So in that sense, you are applying a hierarchization, a functional hierarchy. In other terms, you may say that you are doing a functional decomposition. Okay, so you decompose the high-level function into subfunctions. Here, what is done, just to conclude the idea of iDEX 0, what is done typically is you start from a so-called context diagram. It's like the root of a number of diagrams that can come out from the hierarchization. Okay, we start from the root. In the root, the context diagram, there is only one function. That's the root. So in this only one function means, okay, this function contains a number of elementary activities. This will be specified in another diagram. The diagram is the whole thing, is like a blackboard with a number of elements inside. So this is from the context diagram, you break out the single function into a diagram that contains more functions as a breakout. Okay? So as you see there. So we move from context to child diagram. There is a childhood relationship between the diagrams. Okay? Of course, you can have more hierarchical levels. So if you need more detailed description, this function A2, which is found in this child diagram, may be broken down into some function inside another child diagram. So you are having this here. Clear? In the roots, there is a system for indexing the different activities, A0, A1, A2. Let me say, without details, that this follows the hierarchization. It's obvious that, maybe, it's not obvious having A0, but if you think A2, you may understand that it's obvious that the breakout will be A21, A22, and so on. Okay? So in that sense, you have some indexing of the single functions. You are having also an indexing system for the diagram. Also, the diagram have their own, let's say, index. The child diagram is taking the name of the function that is the origin. Okay, so the index. Sorry, not the name, the index. Names are written here, are written inside the box. This is not generally defined in the sense that the only rule you have to conform to is the fact that typically is a verb, is an action, is an activity, so it's a verb, cut. But the meaning, which is not the syntax, is the semantic, the meaning you give depends on the domain. Cutting has a meaning, but in another place it's driving. No? Depends on the system. Okay? So you understand that it's quite simple. One modeling comes from the box, repeated in iterative sense, errors that relate to the box and functional decomposition. And that's the good, let's say, property of iDEX. I told you some other methods. Of course, I presume that you can have also the recording if you are missing something, and of course you have the link if you want to apply it. Yeah, it's quite simple. By the way, let me say this, but this is valid for other languages. You may have tools to make this kind of scheme. For example, in Microsoft, there are certain tools that support iDEX 0, but there are others. You can find, of course, open tools in the web, so there is everything. At the end, it's a standard language, so you may understand that when you're scheming out, maybe the software tool can have some, maybe because it depends on the tool you're using, it can have some let's say, capability to verify the syntax, if it's correct. Okay? But this depends on the software. So, the idea of iDEX 0 at this stage is to transfer to you some method that relates to the system engineering. We said when we state a function, so this high-level function in the context diagram, it's like saying we're basically fixing the function that could be studied. maybe it's good also to think that because of the iterative process, this function is not enough to have a specification of what you're going to study. You may break down by just one level, because more levels of hierarchization means more detail, which is not the case in the real beginning. Okay? So let me say that level 0, the root, eventually one level down, could be the case of high-level functions representation. Okay, no more. It could be even only level 0. So this one, I cannot give you a general rule. Come to only this one, because there is another consideration to divide the different context of representation in IDF 0. That you can have different hierarchy, not only one. So what means different hierarchies? You have a context diagram A minus 0 that has a name, and another context diagram that is A minus 1 as another name. Okay? Each of them are context diagram, the top level. They are not being broken down, but they are two contexts that will be detailed later. But defining the context diagrams, more than one, you're fixing the boundaries. To understand in principle, here you see a context diagram because it's the functional box at a high level. It's here. This context diagram is could be the only focus of your work, maybe. I don't know. In some way, it is telling you with this clause not only the functional box, but also the boundaries. There are some input and output. Okay, so you see the boundaries in terms of functional flows related to the function, not only the function itself. Okay, look at what is written. Of course, my statement was general. Then give the meaning. It's a gearbox manufacturing, so probably it's a production plant. If you see the different arrows, the arrows, by the way, this is typically a verb, manufacture the gearbox. I'm not saying that always I'm using the correct syntax. But these others are typically nouns, so operators, machines, whatever. So you understand that the manufacturer of gearbox is adopting a number of resources, different types of resources, from human, physical resources, also operators, to informative resources. MRP is the information system. So let's say a method that can be implemented in the information system. Okay, so if you see here, if you understand the domain, maybe it's not your domain, but one may get the understanding that we're talking about a single production plant. Operators together with the shop floor system, which is something that is controlling the flow in the system, the advancement of the production, the MRP, which is about planning, but for this company. Okay? So you're giving the meaning by reading also the arrows. And so when you're giving the meaning, you're like understanding the variables within the boundaries or out of the boundaries. Okay? So it's a matter of boundary in the future. Here, can you follow this? So you use a method to have a graphical picture of the boundary. So I understand that, of course, the boundary starts from some material or information flows that relates to the outside world, not my content, others, raw materials, purchased items, orders, and so on. These are input. I understand that there are some output that goes to the outside world, what I produce. And I understand that there are some other particular flows that probably relates to some constraints, shop capacity, goals to reach manufacturing objectives. So this is kind of driver for the manufacturing of the vehicles. Okay? So this is just to use the example to say what? That this could be, let's say, the definition in the context diagram of the boundary of my work. I look at the gearbox manufacturing plant with its own resources, having some limit with respect to the other. Okay? If this is the case, this work is related to improve, or at least analyze and improve the organizational system within the manufacturing of the gearbox. But just to think about a little bit beyond this example, only think, okay, I'm not looking only at the single plant, but a supply chain. Okay, so you may think that beside this context diagram, we have another context diagram, the one of the supplier. Maybe first the supply level of suppliers, no more than that. So in that sense, we have two context diagrams to fix, let's say, the boundaries which are not only related to my plant, but the supplier plant. Here, so this tells you a sense in terms of functional modeling of this organizational system. Is that clear? And this tells you also the sense that boundaries in some way are defined by high-level functions. You may decide the level in the hierarchization. Of course, let me say no more than one level down, because there we are detailing. No? The more you go down, the more you are detailing. Here, so this is the functional modeling, but it's not enough. It's good to mention also that in a context diagram, you may have two statements. It's textual description. The statement of the purpose and the statement of the viewport. In item 0, purpose is exactly coincident with the meaning I told you. Is a statement of the reason why I'm committing to making a study of system and engineering, re-engineering the system. So you see, purpose integration of customer order, processing, and production planning. So the purpose in this case is for sure related to information system, because customer order processing probably may have some part of the information system which is not well integrated with what is tracking the production. You know that from the point of view of production planning, of course, we need some, let's say, flows from the orders, sales forecast in general, to have the production plans. If the purpose is written there to integrate, I would imagine that the problem is that we're having some lack of integration between existing systems. So people are doing a lot of job like manually moving the information or inputting question. So thinking about integration, of course, you are moving to some automatic transfer of information from customer order processing to production. So it's clear that when you're using item 0 and you have the context diagram, you can have a possibility to make a statement of the purpose. Okay? Second, you have a statement that is particularly, let's say, the meaning is not so clear. Maybe viewpoint is the perspective of the stakeholders. So here in a list, what is the perspective? What are the stakeholders for which you want to get a perspective? So an involvement, an engagement. We want to talk with sales experts, logistics people, production planning department. These are the three, say, roles in the organization which represent the main stakeholder of my analysis. So they will be the one that would be involved in some interviews, some consensus in the functional. Okay? Here. So this gives you a very simple technique. You have the functional modeling perspective. You break out into functions. You think about flows around the function, and these flows are kind of interfaces through different functions. Because one flow is an input that comes from another function. It's an output. Okay? So, not new, sorry, new for you, but nothing special, I would say. It's simple. Maybe you can see if there's utility for some reasons. I've been using it a lot. I've been using it to start to analyze production, let's say, management processes in companies in different functions. Maintenance, production functions, typically, it's my domain of work and this. I recently used it within PhD work where we are studying, still running, but we're studying the introduction of say optical sensors in a part of an helicopter. The helicopter is the technical system, the part of the helicopter is the technical system. The optical sensors are of course, the subsystem that is inserted here. The reason why we're doing this is to enable a capability to, let's say, measure and monitor some information about this critical component, even in the production stage, up to the user stage. So it's like having some measurement that is integrating this information from the moment it is made, the moment it is used. Because it's critical. If it breaks down, of course, the helicopter falls down. Okay? This is just to tell you the context. The either zero was used in reality to express the different activities that are done and how these activities are changing through the introduction of this sensor in the reality. So what is done now, what will be done in the future with this optical system, solid sensor. So it's, if you think about the application, it's about talking about what we're doing in an organization, in reality across organizations, because it's the builder of the helicopter, but also it's the user. And thinking about how these optical sensors may act and may enable a change in the process. This is not the final goal, but just to tell you that this analysis was useful for the final goal. The final goal relates to understanding the cost and benefit of this system. So the analysis helps to make some life cycle cost. No more than that, but just to tell you a practical sense of the fact that this is a simple analysis, but you may imagine that the diagrams are not so simple because there are a lot of activities in the production, certification, helicopters, testing, and so on. So on. Okay, having a formalization of this, when I understood that this was the case, it's clearly powerful issue because you can discuss about some formal thing about the real cost, because otherwise you have barriers. You may think, okay, we have a norm, we cannot change anything. That's the point. Remember, aeronautics, helicopters in particular, this case have norms that, of course, are very important and so prevent from changing so much. Here, so let's talk about this one, seeing what is happening in the process really, and what are the costs and benefits. Okay? So this example, it was just to give a tangible sense of the use of either zero. Let's go back to the main flow of my reasoning. Now we are in the first stages, identification and concept. So saying that we fix two context diagrams, and for each of them we have a hierarchization at a second level, is like saying we fix the boundaries and made the definition of the diagram. Okay? Here, another way to make it, maybe describe it in a different ways. It's another method. Let me say that I will be quicker because the meaning of boundary definition and so on was already discussed. So you will find the correspondent representation here, nothing new. The novelty I would like to remark is about the way you see the problem, the system. The way you see the system is not, let's say, driven by functions, but driven by so-called processes. I would like to distinguish a little bit what I mean for function and process. Of course, it's a distinction that relies on some, say, some literature, some background. Let me also say that sometimes the use in terms of common terms is a little bit sparse. So sometimes you talk about the process, but you mean a functional perspective. So it's a little bit, let's say there is a mix. And quite clear that I want to talk about business process, process in general. There is a connection to a functional perspective, but if I rely on this, what is a process? Let's give a meaning. The process is basically, so here you see as an acronym DP, the main process. Process is something that is delimited by events. So there is an event that starts the process. There is one or more events that determines the end of the process. Event is exactly the concept you have from discrete event simulation. We already discussed it with Elisa. Comes from, in general, not only from discrete event simulation, discrete theory, discretization of a system. Event, just to remember a little bit the concept, is something that is happening and determine the change of a status of one or more entity in the system. Status is a situation where you can consider say, a situation where you are in a kind of stability. You are in that status. The piece is working on a machine. Of course, it's working. There is a dynamic there. But from the discretization, you may think that it's working until it ends. The end of the working stage is the event that determines the change of the state. You remember this? We discussed it with Elisa. But also, if it's not ending with the end of the working activity, it can end because the machine is failing. The event of failure is an event. So, said this, you know already the general meaning of event. Now I'm telling you about the meaning applied to process. Process is something that is triggered, activated by one or more events. You have the meaning of event. And that's up with one or more events. So the driving concept of building a business process are events. In between, you can have intermediate events, and you can have functions. So when I'm think about the double perspective, when I'm making processing of a workpiece on a machine, if you think from the functional perspective, processing is a function. Okay? But if you think that this processing starts after an event, it is part of the process. In the definition you see here, starting from this language. Okay? So the discretization is absolutely important to, let's say, create a course of action, let me say, a path through events and functions. The course of action or paths through events and functions, like saying, we see the process evolving over time. Event, function, event, function is like seeing in time what is happening. Okay? So the distinction I take from this language is exactly this. To me, I will rely on this. To me, process is something that can be understood because we have some events that are enabling to understand the timing. The fact that it's evolving with time. Okay? Do you have any question?
Yeah, can you repeat the discretization fundamental importance?
I repeat, but I invite just to use an example to understand. The example. just representing a timeline. So an axis in time, not to make it in a formal language, in the sense of graph, but just to think the. Let's say that we have start production in machine. This is an event. Let's follow a piece. The piece is going through events, start production, end production, start the quality control, let's say, end the quality control, and so on. Between events, there is some time, there is a period of time that is passing. Okay? So, this representation tells you something that relates to timeline, first, and the timeline is tracked through a sequence of events. Okay? Can you follow this? There is a timeline and a sequence of events. But this is a possible history. Let's say that the next event is end delivery to the customer. Okay? This is a possible history, successful one. You're delivering to the customer. Okay? But another kind of realization could be that after the end quality control, we discovered that it's a deficit. We're not delivering to the customer. So the difference in this possible timeline is start the repair action, for example. Another event. So you have basically two realizations, one or the other. Was not representing the two timelines, just you understand. Two realization of the same process. To me, it's the same process from the point of view of logic. Think about the logic. Think about that the complex system should be understood through the logic that is behind the system. The logic is driven by the events and some information related to the event. Can you follow this? What is in this logic? What is important in this case? The information related to the end quality control. It may determine that it moves to the delivery of the customer or moves to a repair. Okay. Here. So two realizations of the same process. You not fully understand because I was not expressing in detail something like that. But when you have the full sense of the business process, it's because you have the events. It's because you have events means something that relates to time. The sequence, and again, it relates to time because the realization time of events, it's like saying that you have seen a process in its execution. Okay? Through events. Third, but not less important, there are some decision logic. There are some decision points depending on the event that are happening and the information related. So, timing, sequencing, and decision logic. Where is the decision logic in my example? It's related to the end quality control. In the event, associated to this event, you may have a label on the piece that says it's good or not. That's the information event. Okay? And depending on this, you may follow different flows. Is that clear? As a logic, you will see now in the modeling method more in detail. So we are taking the same consideration. But the business process, the process, I will not say business is an application. It can happen also to a technical system, production system, whatever product. A process is Related to time, and in discrete theory, you may use event to have an instant in time that is important to fix some element in time. Related to sequence. Sequence of what? You can see again in terms of events, but also in terms of functions, because an event relates to a function. When you're working, you determine the end work. When you're repairing, you determine the end repairing. Okay? But time and sequence basically tells you realization through time. Then there is what we could call decision logic, in the sense that you have some logical consideration that tells you that your process will continue in one path or another path, depending on what happened. Okay? What happened means depending on the fact that the event happened and brought to some new status. Can you follow this case? Think about the case, the end quality control will bring him to a new status for the product, good or defective. Event relates always to status. Okay? So when you describe from the point of view of event, at this level, which is not detailed, the detailed level will be analyzed later. But at this level, it's simply thinking we have a boundary. So from one event that is the starting point to the event that is the end of the world. So there are events that delimits the boundaries. I tell you a case, an example. Think about the production planning. Okay? So here could be this one. Generate manufacturing plan. Starts with some say timing that depends on the clock. Every beginning of the month. This is the end. Every beginning of the month I generated the new manufacturing. So the clock in time. It's the end. Okay? Ends up when you succeeded in generating the plan that is visible. And the result, the event is visible plan. Is the final status after some elaboration that maybe have required some reworking. I don't know. I do not look at the detail in between. I'm saying that I'm ending with an event that tells you the process is ended. Okay? Here. So, in a common sense, you may say the event is something that generated, let's say, an issue to be resolved. The end event is the final result of the solution. Would be also not okay, not feasible, but you ended up the process. Okay? Here. So, what I'm thinking in this, so it required a little bit some time to think about the distinction between function and processes, at least in the definition that comes from this. To tell you the origin, SIM stands for Computer Integrated Manufacturing, also stands for Open System Architecture. It was historically developed before other kind of architectures, like the JRAM that I mentioned yesterday. It was related to the idea of having manufacturing integrated by computers with no people inside of the factory. It was in the 80s. And of course, you may think that the integration depends on exchanges in the idea between computers, which means synchronization. So a process is executed through computers. Think about the vision, SIM, by means of events that determines such process. Okay? So in each computer you have some coding that makes the activity, and the events rule the sequence of this activity. Just to give you a general idea. Can you follow this? So of course this was the origin. we can learn today the idea of discretization applied in terms of processes, generally, not only for computer systems. Valid for hospitals, it's valid for manufacturing systems, it's valid for telecommunication networks, it's valid for maintenance activities. Okay? So, in terms of boundaries, the language of Simosa provide you a simple graphical template like these ellipses, where you contain a number of domain processes, the one you believe that are key to the boundary you are talking about. Remember the consideration of, yes, key variables are those that are important for the functions. Here, the key variables are the domain processes. Okay? So, DP3, DP4 relate to the generation or reworking for some reason of the manufacturer. In the graphical representation of Simosa, the ellipses that are colored in gray are those that are important within the domain, so within the boundaries. So we see that the domain DM 1, 2, and 3 are those domains that contain the processes that are relevant for the analysis later. These are given the boundaries. So we have DP1, 2, 3, and 4, and 5, the processes that should be analyzed in details later on, because there we have the key variables for some improvement, some system arrangement. Okay? Others, the one in white, also with this kind of line, are those that are at the interface. They are not in the boundary. They are in the environmental context. Of course, engineering may be influenced for, so DM5 may be influenced for DM1 and DM2, but we are not analyzing. We are analyzing at the interface. Okay? To conclude, not just to conclude the discussion of the picture, interfaces are those given in this, let's say, channel between the domains. You see OV that stands for object view. You see EV that stands for event. The event are those that are the one that you may think of when you talk about the processes. So, in other ways, each process may have, is not written here, may have events that determine the start of the process and events that correspond to the ends. Termination. Each of them is not written. But this starting and ending event can be also seen at the interfaces between domains. So the flow in terms of event means that this EV2 and EV3 comes from TM2 or TM3. Now we have to look at the meaning. You know? But one is generated by one domain and sent to the other. Okay? Of course, there could be a more formal way to say what is the destination or what is the source, but imagine like tables, no more than tables. Template, let's say, source event, destination of the domains. Okay? It's more historical reference, but rather than maybe applicative today. But it was because I believe that this was giving you, this was giving me first, and then be helpful for you to think about the understanding of a process, something that is executed through events. Think about computer integrated manufacturing. Think about computer system. Okay? So this is just a summary. An event occurs when one or more entities change the status. Some example. If my phone is ringing, is an event, but I can't answer. End to end. End to end is exactly from triggering event, the one that starts the process, to the ending result, which is the final ending. Even like not okay, I'm pushing the no answer. It's the end of it. A domain may contain one or more process. I was writing also this one is like a metaphor to say if you look at each domain, with the domain process, it's like having a table of content in an index of something that tells you what will be described in that book. We will talk about 5 processes. Here, director. That's it. I think one or the other could be ways to represent the boundaries. If you take more the functional perspective, you don't think about events. Either zero I was not detailed with either zero, I will be now, but the event as a constant is not in either zero. Either zero has more an interest on the flows, input output, but not on the timing. Simosa is more related to events, for sure. Okay? So this reasoning function between process versus process is still maintained later. So we continue a little bit. In this moment, remember that now I was canceling, but remember that we are discussing basically about the boundaries, the functional definition. So we are in the high level stage here, identification concept. I will skip a little bit now the consideration of values. I move directly to here because it's somehow logically related to the discussion that distinguishes between function and process. Then we will move back to this, so we'll go back to the life cycle perspective, but I skip a little, okay? So we can conclude the reasoning and then we can make a break. So I skip this one. So I go directly to a phase where, in terms of life cycle model, let me say something about that. We are basically breaking down up to more details. From high-level functions, we break down to elementary activities and tasks, which tells you more about the details of the process or the function. So the idea of hierarchization is valid for both the 2 views. Sometimes this kind of language talk about view, modeling view, because it's a general consideration. A modeling language enables to express typically some aspects of the system and not others. The system. Of course, you may see that somehow the expression that I will show you now are a little bit different, exactly because there is a different view that you look at into the system, a different perspective. So function analysis, so function view, is represented by the 0 as example. So I will take a little bit of the 0. I'll give you some further details, but the main consideration of either 0 were already given. Just a little bit a remark. Functional modeling means that we look at the functional transformation that is performed or supported by the system. This was already discussed. The main interest is that we want to see what is the outcome of the transformation, knowing that we start from some factors that are required for the function, already said. Here I'm distinguishing a little bit inputs plus other conditions, because I will be more precise with respect to previous consideration. I will clarify what means the flow, let's say, on the left part of the box, the flow from the top, the flow from the bottom. These are different flows. Let's say, in general, input, to be more precise, are input plus other kind of flows. So I will be more precise in this. But in these flows, we look more at, let me say, at what I need to perform without having a specific insight on the timing. That's the point. So it's a functional. So this is the same function box we discussed before. So the verb could be the name of the function. There is an indexing system. There are some nouns that can be used to label the errors. In a short acronym, we are talking about ICOM flows. ICOM, input, control, output, and mechanism, which are, let's say, related to the different position with respect to the function. What is the input? The input that enters to the left. What is the input? Is the object that is subject to the transformation. If I disassemble this, the input was my pen, was my. It's not a pen. Something else. Okay. This disassembly is the function I'm doing. This is the input that is transformed. Okay? Of course, the transformation input, the object that is transformed, comes as an output with different properties. Here we have two components. Okay? So, these are the outputs. The mechanism is typically what is supporting the function. I am the mechanism. I'm doing the disassembly. Okay? And then the control. The control is any kind of, let's say, instruction, order in terms of command, order in terms of guidance, direction, and so on. Something that, let's say, is required to carry out the function. Think about this. I should have the knowledge that to disassemble, I have to move in this way. I need to have this knowledge. Not this way. I cannot. Knowing this enables to make the activity, the control is required. But of course, if you know about that, but you don't have myself in the activity, I cannot disassemble. So the whole factors, these three are required with different roles. So this is telling you the role. Depending on the position where you place it, there's a different role with respect to the function. Okay? I am the resource of the mechanism doing this. This is the input and it will become the output. The instruction to make the disassembly is the control. Okay? Different roles. Of course, it is, I would say that we confirm that it is simple, because at the end it's easy to see what it means. Here it's a summary of what I told you. Applied work to informative and material flows. You can think about energy flows, you can think financial flows. So this is the example related to these flows. So you see that, for example, having a master production schedule, which is a planned production plan, is typically a control if you think about the production. Okay? Having an equipment, a machine, an operator, a database could be mechanisms that support an activity. Here, it's the summary of what I told you in the sense of example. If you have this one, it's repeated in different decomposition level. This is the breakout that comes from the high-level function. So, to remark what is happening, of course, this is the hierarchization. We move from the context diagram where we have one only function, and we move to the child diagram where we have more functions decaying, the only function. Okay? But it's not only breaking down in function, it's also breaking down in flows. If you see from the point of view of the flows, let's take this one. This is generally saying it's the process plan. So of course, if one related to this label, the semantic of a process plan, you may think that it's probably a list of operations to be done with some information on the way to do that, the production. That's the process. That's in this level, it says just we need the control for the produced mechanical part, which is the process plan. But later, if you break down, the process plan is disaggregated in specific flows. We need to have cutting, drilling, or milling parameters destinated to the specific function. Cut, drill, and mill. This is obvious, no? We are distributing the proper parameter to the specific function. So this is not to enter into the example, but just to say that these flows are also detailed. You may see that there are different details. For example, in this way, different ways to express the details. But this relates to the logic that you may apply in these flows. You see that the worker is here labeled and here is not. You see that the machine here is labeled and here is labeled. So in this, there is some logic that you can find in details in the IDEF 0. But in principle, let me summarize here. Basically, when you're having an error that is branching or an error that results as a join, so what you see here, here you see the branching, the cases of branching. The labeling rule may be a little bit different if you want to express something which is a logic of mutually exclusive flows and others which are. You can find examples, you can see if you want to be precise in this, but basically it tells you some logic with respect to what you may have in the logical system. Without details, but let me say, just using the example, just to give you a meaning. In principle, if you see here, we have machine, which is the pool of machines of different types. But then if you see, the machines are specialized. And the different specialization, one is not excluding the other. Each of them is having a destination, the specific function. Okay? So in principle, I repeat, this is not representing time, but if you think the other view, in terms of time, in principle, you may have one milling machine working, one cutting machine working at the same time. No? Okay? Even if this is not time related, but you are having the function. In this other case, we have a pool of workers, but you see that there is not cutting worker or drilling worker. There is no level. So you may think that the worker is capable to make the whole things. But the single worker cannot be in the same place. You think about that. Again, it's not the objective representing the time, but it's the logic. The single worker can work on the tools, being probably polyvalent resource. But of course, you cannot be concurrent in the two. Okay? So you have the impression of what it means, the logic with this branching, you see. I skip a little bit this because somehow we already said that, but I go directly to this. IDEF 3 is another perspective in this set of IDEF 0 methods, IDEF methods, sorry, because IDEF 0 is one method, IDEF suite of methods is telling others, is more related to processes, but I could skip directly, maybe I could tell you a little bit some consideration later, I go directly here. This comes from the business process modeling, this the origin. It has a number of constructs which are this symbolism. The one that are, let's say, the major construct that relates to the process view, those one. So just the function, it's a box, It's a rectangle. So if you see from the point of view of function, it's nothing different with respect to the idea. It's a function. Something that transforms an input into output. Same thing. Okay? But if you want to have a process view, the only interest is to create a chain between events and function. You saw here, released in time, over time, the chain. Start production, end production, start quality control, end quality control, and the activities in between. There is a chain, okay, of events and activities or quality function. Okay? And of course, if there was another case, the case of ending the quality control with defect, there was another realization, but in terms of logic of the same chain, just another output. Okay? So remember that we're interested in time and sequence and decision logic. So time and sequence somehow comes out from reading the path along the event, the function put in a chain. This is the path. Okay? The decision logic are represented by symbols and or and so on. So this decision logic applies to what? To the events, to the function you find in the chain. Others tell you a little bit another consideration, but I will conclude it later. So I move directly to the representation first with scheme, error scheme. You see the start event. You see the end event. Remember that we can have more than one. In this picture, there is only one. You see that there's a part of events and functions that can be realized through time. That's whatever it is. So the event is happening in a given moment in time, start, the function is operated, and then the outcome and the logic is that we start two other sequences. After we have ended with this function, we're having two events, E1 and E2. These are intermediate events. It's just a generic example. And so on. If you look at the specific example, see this one, just to think about the meaning. And let me also say that here you may have event or what we could call the condition that is, let's say, the ending status that represents the condition that is discriminant to understand that you have to follow. Let me discuss a little bit. So, event or ending status may be represented in this picture, in this symbolism. Let's read this through the example. It relates to a warehouse and the process of receival of goods. Of course, the process starts every time a truck arrives, there is an arrival of goods. This is clearly an event. We have a truck entering into our factory, into our warehouse. This activates, after the event, we may think that, of course, there is some function to be activated in the sequence, and it's verified. The verified load may have an outcome, XOR. So the logic is exclusive, mutually exclusive, one or the other. Okay? So the verified load, of course, you may say that the end loading, the end verification of the load is the event. But this is not discrimination. The discrimination comes with the outcome. The loading is okay, the loading is not. So these are information related to the event. They're not the specific event. It's the ending status related to them. It's like the quality control I was mentioning before. It's good or not? Clear? So either it is an event or the ending status associated to the event that represents the condition that is the result corresponding to the event may be in that symbol. Okay, one or the other. So if we're having a loading occasion, this ending status, of course, we trigger the load codes and we're having the end loading. So the good is in the warehouse. Otherwise, not okay. We are just sending a complaint to the supplier. Of course, we could elaborate more on this because it's not only sending a complaint to the supplier, but just to say that we're following this path. Okay? So, more clear now? Because basically, let's go back to recognize the element here. We have time. I see time in the logic because events tell me about time. I'm not seeing specifically in a time scale, but I'm seeing in the logic that represent any kind of realization may happen in the process. Through time, you may have one process that is arrival of good, verify load, loading occurring goes here. This is one realization. And the other is this one. Both the tools are represented by this scale. Okay? So time is given. Sequence is given. I'm reading from top to down in this representation. Vertical sequence. And decision logic is there because we are having the connector logic, and we're having some decision logic that can be written by combining the function and the outcome, which is data entry. So this is the okay. Then one may write also in terms of say pseudo language. It's like if something happens, then. But this is just more, let's say, textual representation. This is the skill. Clear? So I wanted to move quickly to this because it was very much related. Let me say another consideration is this one. Then we can make a break. You can have other symbols in this. This language is even process chain. We can have other symbols, but these symbols are not, say, originally related to the process view. They are more related to the functional view. You can attach them, but it's another perspective. Why? Let me say. The application system, think about in idea 0. It's like the database, like the resource that is doing everything. No? The data maybe is a set of input that they are required to elaborate. An organizational unit is a resource again, right? Responsible for some activity. So, of course, there are more other symbols that relates more to the need of business process modeling. If you see here, for example, in this case, we have related the organizational unit that is execute this activity. Here it's not a matter of time, it's a matter of the fact that you're saying who is doing what. With who responsibility. It's not a matter of time dependence. It's a matter of who is doing this function. In idea 0, it will be set as a method. I am doing this function. Okay? In this, it has another representation. It's a matter of this language. So we can make, okay? From the audience, is that okay? Comments? Questions? Comments? Can we stop here? I mean, for a break? We can stop. I will put in a pause. We can make 15 minutes. So it's up to 50. Okay? 3:50, we are back. 3.